Welcome everybody. This talk contains provocative opinion, so if there is any Intel fan, my sincere apologies to you. I'm not responsible if your blood pressure overshoots, but I am fully responsible for each and everything that I will say in this talk because this has solid scientific foundations and evidence. So let's get started with the Intel's Security First Pledge, which says that the security of our products is one of our most important priorities. Cool. We strive to design, manufacture, and sell the world's most secure technology products. Right, so this talk is going to be about one of such world's most secure technology product, and more specifically, I will present understanding trust assumptions for attestation in confidential computing. I am Usama, and I will present here the research that has been carried out in the doctoral thesis so far and some directions which are being pursued. The promise of the talk is as follows, that during the last decades, it has been figured out that complexity is the worst enemy of security. And it really is like that. So when we have a very complex system, it's very difficult to debug it. It's very difficult to understand what is going on, and it leads to different security flaws. However, it seems that Intel has not learned the lessons from the failures of SGX, and its recent technology, it's repeating the same complexity problem. So there is a lot of chaos in the Intel specification of attestation that I will describe in detail. More specifically, the things are not properly specified, and this leads to security through obscurity. And secondly, the things which are actually specified contradict each other, contradict at other specifications in other documents of Intel. So there is a need for perspicuity and formal guarantees by which one can guarantee that the system specification, the implementation of the system actually meets these specifications. And thus we had this research question to start with, that can we verify the claims of Intel, more specifically about the attestation process inside the Intel's trusted execution environments? And if yes, then how? And it would lead to explicitly stating all the trust assumptions that are used in the proofs. And this is really helpful because based on these trust assumptions, we can then see how we can, or whether we can first minimize trust and maximize the trustworthiness. Trust has multiple meanings. Here I specifically use the one used as in Basin et al. And this basically I want to describe that how can, if it's possible to minimize the trust in this trusted execution environments attestation process, then how? So to achieve this promise, I have this outline that I want to introduce to take everyone on board. What is trust? What is confidential computing? And what is specifically this mechanism called attestation? And then I will describe about one specific trusted execution environment offering of Intel, which is the next generation offering, Intel TDX Trust Domain Extensions. And I will present three specific examples of this attestation process, which I described in the promise that where the chaos exists, and what things are specifically underspecified and what things contradict each other, with very simple examples which are easy to understand and know. So symbolic security analysis is what we use for the formal specification of the protocols inside the attestation process. And then finally, I will summarize the talk. So trust, as I said, has multiple, even contradicting meanings. And the one I use is as follows, that what the user wants, basically the user of any system has some specific expectations of the behavior of the system. And what we want is that the behavior of the system should satisfy the user's expectations. And there are like two kinds of systems. One is trusted system, where we assume or hope that everything is working fine. A better way of doing this is to have a trustworthy system where we actually validate or justify that the system's specifications actually meet the user's expectations. And this is at a layman level really like these security gates that we pass through during travel. So the idea of trusted is something like you are good to go, you don't need to pass through these gates, your luggage is good to go, you do not need to pass it through these scanners, and everything is good, you do not need to pass through these. And trustworthy is that we actually pass you through this gate and scan the luggage and then check that everything was fine, and if there is some doubt, then manually check everything that everything is working fine. So this is the idea of trusted and trustworthy systems that I will use in this presentation. And the way to achieve from moving from trusted to trustworthy systems is to have a rigorous proof by which one can validate that the assumptions, that the specifications are actually met. So confidential computing basically is a part of secure computing, where there are two high-level classes. One is purely algorithmic, and in that specific class there is homomorphic encryption and secure multi-party computation, and these are comparatively, they have lower trusted computing base as compared to the hardware-based ones, where we actually need to trust at least one layer of the software in addition to the hardware. So this specific part of the secure computing is known as confidential computing. And as I said, there is a specific assumption that we trust the hardware and at least one software layer, and that's why it has more trust. And in order to overcome this trust, basically we need to have a process or a mechanism which is called as attestation. And I would argue that this is actually the most important mechanism of confidential computing, because there is no cryptographic assurance whatsoever without this process of attestation. And let's see what the argument is of the critics. More specifically, I'm not aware of any anybody from scientific community who disagrees with the importance of attestation. The only specific one that I know of is the Confidential Computing Consortium Technical Advisory Committee, and what they say is they do not have any scientific argument against this. So they do acknowledge the importance of of attestation in confidential computing. However, due to their political reasons, they do not admit that it is one of the most important mechanisms of confidential computing. As I said, even the critics do admit its importance, and this is the statement from their white paper, which says that any attack that could compromise the attestation of a TEE instance could lead to a workload or data being compromised in turn. So this clearly states the importance of attestation, that even the critics also admit that this is really important, and once attestation is compromised, everything is compromised. So let's look at Intel's trusted execution environments. As I said, the focus of my research has been on Intel's trusted execution environments, and at a very high level, the trusted execution environments can be thought of as two classes of, one is process-based and the other one is VM-based. Process-based has the advantage of having a smaller TCB, whereas the VM-based provides the ease of use. In the process-based category, Intel has this solution called Software Guard Extension since 2014. And in 2020, Intel announced the specifications for VM-based solution called Trust Domain Extensions. In Intel SGX specifically, the remote attestation process is of two types. The first one is called EPID-based, Enhanced Privacy Identification, and the second one is called Data Center Attestation Primitives. The remote attestation process inside TDX has major differences as compared to Software Guard Extension remote attestation. The first one is different report generation mechanism, that is as compared to SGX. And secondly, it also needs, in addition to the static time measurements, it also needs the runtime measurements, because it's a whole VM and whatever is being added to the VM is required to be measured. So I will now describe about the Intel's attestation process inside trust domain extensions with three examples. As I said, clarifying why I say that there is a chaos in the specifications of Intel, what things are really contradicting and what things are underspecified. So these are three very simple examples that, as I said, you can understand without having in-depth knowledge of Intel TDX. So the first example is like this. This is the figure from Intel's architecture specification. And the first thing I want to talk about is this structure called TCB info. As you see, this has 4 fields. And in another document, which is again from Intel, that describes that this structure has 6 fields and the hash is taken over all of the 6 fields. Similarly, for this TD info hash, here in this specification, this is shown to be having the hash of this structure is taken only up to this field, which is XFAM, in a different order, and in another document they describe that the hash is taken over the full structure, full data structure, which is in another order. And thirdly, and most importantly, the only description of the code structure, which is here, this figure is the only figure which describe, or even in documentation, it's the only description of the code structure, which is actually the most important structure which is used and sent over to the relying party. And however, this is strange that Intel has only described this structure only in this figure with only a few fields, which has many missing fields which should be there for the whole structure to make sense. So we reported the issues to Intel in April 2021, and I would like to describe firstly this just as an example, that figure 10.1 of 41 that I just described shows that this SHA-384 hash is taken over 4 fields, the four fields of that structure that I just described in a specific order, whereas the seam leaf operation in 11, which is another document or specification document of Intel, shows that the hash is taken over the whole data structure in a completely different order given in this table. It is worth pointing that the order matters for hash computation. So it's really clear that there is this contradiction, and Intel acknowledged and promised to update the specifications of all that we described in our paper. And here is what actually happened afterwards. This is the updated form of Intel specification after this. And let's see closely what actually they changed. So what happens here is that this TCB info exactly remains the same. So these are the 4 fields in the same order. The code structure that I described remains the same. And the TD info structure, which has actually changed a little bit, is still inconsistent with what is described in another document of Intel specification. So it's really unclear that why these changes could not be made to this specification documents, even though we had very clearly described that these flaws exist. Right, so next example I want to describe about trust boundaries, what is trusted by the trust domain and what is not trusted by the trust domain. So Intel claims that basically the trust domain, the things which are trusted by the trust domain are Intel TDX module, the ACM module, and TD coating enclave and Intel CPU hardware. But Intel never describes that how the secure channel is established with another enclave, which is called provisioning certification enclave during the provisioning process. Because according to this diagram or specification, all other software is to be considered not trusted by the trust domain. And this entity is really important because this enclave bootstraps the process of attestation, and it's going to provide all the security certificates and so on. So the chain starts with this entity. Right, so let's move to the verification side, the verifier, when it's going to verify that. And this is again a very colorful diagram of Intel, and let's focus on this part, which says that the platform certificate key, the PCK certificate basically is Intel root key signed. However, this is not correct, and this should not be signed by the Intel root key. It should actually be signed by the key which belongs to the Intel SGX PCK certificate authority, or the Intel SGX PCK processor certificate authority, depending on which scenario we are in, as is clearly available from this another specification document of Intel. So I have here a diagram which clearly describes the chain of trust for a single package platform in Intel TDX. And more specifically, I have here the chain of trust starting from the root CA up till the trust domain. And here in the reds, all the descriptions in the red basically represent private keys or private information, and the ones in blue represent the public keys or public information. And these green symbols represent that these boxes represent the certificates which are in X509 standard format, and the ones here in this color is basically representing the custom format Intel certificates. So it's really easy to understand this figure that this is the entity, this is the corresponding certificate to that, and then it corresponds up to that, up to the end of the trust, it goes up to the trust domain, and the corresponding certificate-like structure of this is called as quote, and this is the final structure that will be sent over to the relying party, and one which has all the information. All of these certificates can actually then verify that the chain of trust is actually correct. So this is more description of, and I should really mention that the custom certificates, that is the AK certificate and quote, I already described that it's not mentioned anywhere in Intel specification what exactly is the format of this quote structure. Same applies to this attestation key certificate, and like there is no description whatsoever of what exactly this is. It goes like it has Intel statement goes like its certificate like structure, but it's not clear what exactly is there. So it's a work in progress that we are analyzing, and we are looking into it. According to our understanding so far, basically this certificate consists of certificate in general, like the very core idea is that it has the public key. Again, the things in the blue represent this public information, and the things in the red represent the private information. So this is the public key for any certificate of A. It has its public key, it has its identity, and then both of these entities are binded together by the signature via the certificate authority. So let's see here from the implementation what we have from the data center attestation primitives. The understanding so far is that the structure contains this public key which is corresponding to this thing. The second thing, which is the identity, in our understanding, basically this is representing the MR signer, and then basically we need the signature over both of these, and then this public key is the hash is taken and it becomes the part of the report data, and then these two things together are taken over. The signatures are done using the PCK, which is actually the certificate authority of the quoting enclave. Sorry, the PCE is the certificate authority of a quoting enclave, and the corresponding key of provisioning certification enclave is this PCK, provisioning certification key. And then the signatures are then a part of this structure, and this structure we believe that which is a part of the quote itself is representing what is Intel calls as the AK certificate. Right, so I now want to, having described what were the problems, what were the kind of under specifications, and what were the kind of conflicts in attestation of Intel TDX, I now want to describe about the symbolic security analysis that we approach, or the tool that we used for the precise description of the attestation process inside Intel SGX as well as Intel TDX. So there are two state-of-the-art tools, which are namely ProVerif and Tamarin Prover, and we decided to choose the ProVerif for the symbolic security analysis. And in this slide I will describe various reasons of this selection. Compared to Tamarin Prover, ProVerif is more automated, and Tamarin Prover on the other hand relies on the user interaction. And also ProVerif is a good starting point in any case, because Tamarin can accept ProVerif like input, which is via the SEPIC tool, but the other way around is not possible. So ProVerif, in our opinion, is the best first choice to start with. And also there is Addition to the symbolic security analysis, there is this computational security analysis. And the benefit of using ProVerif here is that one can perform the computational security analysis on the same model via using the tool CryptoVerif, which supports the syntax of ProVerif. Hence, there is no need to prove one-to-one correspondence between that, which is not the case for Tamarin. One has to prove in another tool, do the analysis for the computational security analysis. And one of the most important factors is that ProVerif is much faster as compared to Tamarin Prover. And this is especially important because of the recent improvements that have been done and were presented at S&P a couple of weeks ago. For details, please see our papers, which are namely this APIT-based attestation process in SGX and DCAP process, as well as this Intel TDX process. This last one is the most detailed one, in which we describe all details of TDX. I want to now summarize my talk and provide the currently pursued directions. So the take home is that there is really a need to design Intel TDX remote attestation in a systematic way. And this systematic way actually includes a formal proof and formal guarantees, so that one can really believe that it's going to satisfy the assumption, it's going to satisfy the specifications. And we claim that our formal models for remote attestation of Intel's trusted execution environments are at the moment the most detailed ones. The research plan that is being pursued is as follows. I already mentioned that Confidential Computing Consortium has a number of political reasons to market their own solutions, and we had a look at their white papers, and we did their analysis, and we found that their definitions in their white papers are ambiguous, incomplete, and even conflicting. And the security comparison that they have done between different technologies, secure multi-party computation and homomorphic encryption and so on, and also TPM, is neither fair nor scientific. So they just want to promote confidential computing, but they have not done it in a scientific way. So we are working with the Confidential Computing Consortium Technical Advisory Committee in order to make this more scientific and to resolve all the conflicts in the definitions. And this is important because definitions are the most easiest things to adapt and then sell your solutions. So we really need to describe that attestation is a very important process inside this confidential computing. Secondly, we are doing a comparison of the specifications as written by Intel and the implementation that exists. So for TDX, actually there is no implementation yet. But for SGX, we are analyzing that does the implementation actually follow the specification or not, and what are the additional things that are available there, or what things can we extract out from there. As I described, the attestation key certificate is not properly described in the specification, so we are trying to resolve all these conflicts via looking at the implementation. We are also looking at the frameworks, for example, the SCOAN framework, and there is one talk in FAST abstract where we will describe this work in detail. Also, this is really important to impart this research into the teaching curriculum. So we came up with this idea of research-based teaching, where we impart our research, whatever we do in the research, into the teaching curriculum of our systems engineering students, so that not only they learn about the systems engineering concepts, they also learn how to reason about these systems and to develop better systems. And that's why we have we started in 2019 about starting with the attestation process in one of the exercises, and currently we have 12 exercises which focus on attestation and ProVerif for the students to learn about this tool and to reason about the systems that they develop. So these are some of the key references that I have used in this presentation, and these are some more of them. And finally, I would like to have any questions, comments, feedback, or criticism, everything is welcome. And here is my email where you can contact me. Thank you very much.